Um, well, hello everyone, and thank you, Angie, for the introduction. As she said, my name is Alvaro Pajares. I'm working as a product owner at RatedPower. And in today's talk, the idea is to go a bit further on sub-hourly meteorological data and evaluate how does it affect the PV energy yield estimation. The idea is that by the end of this presentation, we'll have like a clearer knowledge about what to expect when simulating sub-hourly simulations. So before going ahead, I will leave you the QR to do put all the questions that okay, so now you hear me? Okay, cool. So, well, you had more time to scan the QR. And well, still I would like to introduce a bit what's gonna be the structure of the presentation. First, we will have a brief introduction about the topic, about the solar resource, and why sub-hourly meteorological data. We're speaking about it today. Then I will go through an analysis that we did at RatedPower, where we evaluated different scenarios, and we will see what were the differences that we found out with sub-hourly sub-hourly and hourly simulations. Then third, we will go a bit deeper into the losses per se, into the differences that we found out, and what's behind that losses and why do we have that differences. And finally, we will gather like some conclusions from the presentation. So going ahead, as we know, when we are simulating the energy production that we can get from a PV plant, there are multiple factors that will affect the final value, the energy yield that we can estimate from our project. And here I listed some of them that will affect the solar resource, the equipment installed and the configuration that we are using, also the design criteria that we are using for our specific project. All the shades that we can get from our PV plant, far shadings, near shades, row-to-row shades, all the shades that we can get in the project, and then some system losses and other losses that we can find in our design. The electrical losses, also the degradation losses, lead losses, and many others. In today's presentation, we are going to focus on the first one, on the solar resource, but why sub-hourly? Well, in the PV industry, we are used to simulate with hourly meteorological data, where we will take hourly values of irradiation, temperature, wind, and we'll simulate hourly time steps. However, nowadays, we are seeing more and more that while the PV energy is more integrated into the grid, we had like more difficult requirements that we will have to face when integrating into the grid. And these grid operators normally will ask more detail about the power or voltage fluctuations that we can have with the energy production. Then also for the battery energy storage systems, we are seeing more and more these systems with PV energy. And there, to get more accurate results, to know better how much energy we can get in the batteries, we may think that we need to go a bit deeper and know better what are the losses that we can take advantage of for the batteries, and we may need to get more granular results. Then another thing will be the effect of clouds on energy production. On this one, we will go a bit deeper later when evaluating the different losses. But when we have more clouds within 1 hour, we can get in and out of the inverter power limit. And so with hourly intervals, we are not considering these fluctuations that happen within 1 hour, and we may underestimate the clipping losses that we have in the production. Then we may expect a higher precision, of course. We are going to more detail. We are simulating more intervals. Instead of 8,760 intervals, we are multiplying that by 60 in the case of 1 minute data, which may look that we are going into higher precision and getting more accurate results. And finally, because we have the availability. Before we didn't have this availability of sub-hourly data, but meteorological data providers are giving more and more this information, so we can use it to estimate the energy yield production. So that being said, now we will go through the analysis that we carried out. So we tried to evaluate what were the differences between simulating with hourly and sub-hourly meteorological data, not only the data, but also all the intervals that are being evaluated. So we will evaluate for 1 minute data, for example, every minute what's the position of the sun, what's the plane of array looking at. All the intervals are being evaluated individually. And we evaluated 5 different locations, Costa Rica, Chile, Finland, Washington, and Spain. Those sites were selected due to the differences in the meteorological data they offer, let's say, like the climates of these locations. Then we evaluated hourly, 15-minute, 5-minute, and 1-minute meteorological data. We decided to evaluate 4 different DCAC radios, to evaluate also how does this affect the inverter clipping losses. For the pitch distance, we adapted it to the location and to the layout, because the idea was not like to optimize this value or to evaluate this value. In terms of equipment, we use a monofacial module, a string inverter, and also tested both trackers and fixed structures. So apart from that, we also evaluated standard layouts, north-south and east-west oriented, but also rotated layouts, evaluating different angles of rotation of these layouts. This means that we evaluated 800 simulations in total, and now we will see what were the results that we observed. So first of all, here we can see a summary of the solar resource that we had in these 5 locations. We can see how some of them, as Costa Rica, has a lot of diffuse, which is like the brown, the brown bars that we can see here, and some others like Chile will have very low presence of diffuse energy because it's like an arid climate, so the amount of diffuse and clouds and rains is quite lower than for Costa Rica. Then Washington and Spain look like more temperate climates. The distributions are quite similar. And for Finland, the distribution is also similar, but we will see that the amount of irradiance is much lower as we are in the Nordics, and also the temperatures are lower. So moving ahead with the first site that I mentioned, the site located in Costa Rica. Here we observed that for the simulations that we ran, always for the case of sub-hourly simulations, we had lower energy production. These values gave us results up to 2.3%, which is quite noticeable. And there also in the graph that we have at the right side of the slide, we can see the distribution of the simulations that we did. So there we have on the x-axis the ranges of percentages of difference with hourly, having hourly simulations as the reference ones. And then in different colors we have 1 minute simulations, 5 minute simulations, and 15-minute simulation. So there we can see how as we go towards 1 minute simulations, the differences in energy production look even higher. So the worst case will be for 1 minute simulation, which is the case that gave us that 2.3%. And when we went a bit into more detail on these losses, like trying to see what gave us that differences in terms of energy production, we observed that there were differences in the irradiation that we had at the plane of array when transposing this irradiance from the horizontal plane to the plane of array for both components, for the beam and diffuse irradiation, and then also in the inverter power limit losses, the clipping losses that is something that, as I mentioned, we were expecting due to the effect of the irradiance fluctuations. So for the beam irradiation, we observed that always for sub-hourly simulations, in this case, there were higher values for sub-hourly simulations, getting differences up to 0.4%. Here we can see the graph, again the same distribution as before, but now all the simulations were on the positive side of the graph, which means that we had lower irradiation for sub-hourly simulations. For the diffuse irradiation, it was the other way around. So we observed negative values always for sub-hourly simulations, getting differences up to minus 0.8%. Then for the inverter power limit losses, as we were expecting, we always had higher losses for sub-hourly simulations, getting values up to minus 1.66%. And there we have also the distribution of these simulations. Now we will go through all the locations that I mentioned. For the second location, which was in Chile, here, even if it was an arid country in which the presence of clouds and rains will be lower than for Costa Rica, we still observed that the inverter power limit losses were always higher for sub-hourly simulations, getting values up to minus 0.6% in terms of energy production. And then also differences were observed for the beam and diffuse components of the irradiation at the plane of array. There the differences were smaller than in the previous case, but the distributions were similar, except for the diffuse irradiation, where we saw that for some simulations we had higher irradiance for sub-hourly, but in others we had lower. Then going to Finland, here we observed a difference in the tendency in terms of beam irradiation. For the previous cases, we always had higher irradiation for the beam component at the plane of array, but for Finland, it's the other way around. So we have lower values for sub-hourly simulations, getting also significant values up to 0.66% of differences. For the diffuse irradiation, it's kind of the same as for Chile. We have some values that are above and below that 0% when comparing to the hourly simulations, but the differences were a bit higher. And also we can see how for 15-minute simulations, which is the bar in blue in the central graph of the slide, how this one will give us lower irradiance, lower diffuse irradiance for the 15-minute simulations, and how for 1 minute and 5-minute simulations we had a higher diffuse irradiation when being compared to hourly simulations. Finally, as before, for the inverter power limit losses, we always had higher losses for sub-hourly simulations. Then for Washington, the tendency is kind of the same as before. We had lower values of irradiation for the beam component at the plane of array for sub-hourly simulations. Same happens with the diffuse irradiation, and the same with inverter power limit losses. So in the end, we observed differences in energy production up to 1.1% of difference when being compared to hourly simulations. Finally, for Spain, again, always we observed always lower energy for sub-hourly simulations. For the beam irradiation, still we observed lower values for the sub-hourly simulations, the same for diffuse, and the same for the inverter power limit losses. So for all the differences that we saw from the analysis, we saw that there were always lower energy for the sub-hourly simulations. So summarizing all of these 5 case studies, in general, we observed always that we had less energy production for sub-hourly simulations. For the clipping losses, we always observe higher clipping losses for sub-hourly simulations. We can see the graph over there. All the bars are at the left side of the graph, which means that when being compared with hourly simulations, we always had higher clipping losses for the sub-hourly ones. And this is directly related to the intervals resolution. As we go to more intervals being evaluated, we have more differences. As we increase the DC-AC ratio, of course, we are getting more clipping losses. So we have also this effect. And with the effect of clouds. So if we go to a climate, to a place in which the presence of clouds is higher, we will observe that the differences with sub-hourly and hourly simulations will be higher in terms of clipping losses. Apart from that, we can also say that we observed differences in the plane of array, on the irradiation that we have available at the plane of array. And there we have the graphs where we can see some cases in which we have lower irradiation for sub-hourly simulations, some others in which we have higher values. And from these specific graphs, we could then know if running sub-hourly simulations will give us more or less irradiation at the plane of array. So with that being said, now we can go to these three different losses that I mentioned in more detail and try to find out what's going on there, why do we have these differences. First of all, about the transposition to the plane of array, when speaking about the beam component, when we are going from the horizontal surface to the plane of array, and we have to convert, let's say, the irradiation that we have at the horizontal plane to that plane, we will use a trigonometrical equation in which, depending on the position of the sun and on the position of the plane of array, we will gain more or less irradiation with respect to the plane of array. So just depending on the position of the sun and on the orientation of the plane of array, we will gain more or less irradiation with respect to the horizontal plane. In that curve over there, I've represented in blue that gain that we can get respect to the horizontal plane with sub-hourly, with 1 minute meteorological data, evaluating for each minute of that day where is the sun position, where is the plane of array position, and what's the gain that we can get. And in orange, I represented the same, but for the hourly interval. So for 1 hour, we are taking the center of the interval and checking what's the sun position. From there, we can see how the curves are different. The one for 1 minute data is much smoother. We have like a continuous line, which seems to be representing better where is the sun at every moment of that hour. That specifically was for a tracker solution for the case of Almeria, Spain, May 15. And we can see how at the beginning we are gaining more because we are like, the tracker is completely oriented to the east, the same at the evening when the sun is going out. And at the center, how we can have just the same irradiation as we have in the plane, in the horizontal surface, which will mean a value of 1 because the tracker is completely flat. So there we can see how the orange curve is like a stairs-like curve, which is following the blue one, but it still has like some steps going from one interval to the other, and makes some kind of weird stuff at the beginning of the day, also late, and maybe in some intervals may not be that representative of the curve. So if we go to specific intervals, these two graphs is like if we had zoomed in that graph at 7 a.m. and 1 p.m. And here we can see how for the 1 minute simulation, we have a gain of 2.5 for the first 35 minutes, more or less, but suddenly we cannot gain that much because the tracker is starting to track, so it's not gaining that much with respect to the flat surface. And so how for the hourly simulation, we were going to the center of the interval, checking the position of the sun and taking that value. So in this specific interval, we are overestimating with hourly simulations how much irradiation we can gain with respect to the horizontal plane. For the second graph, we have the same but for 1 p.m. Here we can see how the value that we are taking for the hourly simulations seems to be like more representative of the whole interval. So we are going linearly with the 1 minute simulation, and for hourly we are taking like the average value kind of the average value for the whole hour. But then also in the last graph, I represented the fluctuations of the irradiance that we can have for one specific hour. This one is for the 7 a.m. and how at half the first 30 minutes had irradiances above the average, but then they go lower. So adding these two consequences when taking the the transposition gain that we can have for sub-hourly and hourly simulations, we can see how hourly is kind of following the same tendency as we have with sub-hourly, but we are not taking like the moment in which we are evaluating the sun position may not be representative of the whole hour. So we may not be representing correctly how much we can gain with respect to the plane of array. This with the factor of that the irradiance is not constant. We have like some fluctuations within 1 hour. These two things make that we have differences when comparing sub-hourly and hourly simulations. It's very difficult to estimate if we are going to have like more irradiation for sub-hourly or hourly simulations, because it will depend on the meteorological data, on the specific site in which we are evaluating the project. But due to these two factors, we will have differences. Then when going to the beam component, here the equations that we use follow the idea of the simplified Perez model. We have more parameters to consider here, more factors. This is an empirical equation which will depend on the sun position, also on the orientation of the plane of array, but in addition to some coefficients which depends on the diffuse horizontal irradiance. This graph that we have at the right side will represent the same as before, but for the diffuse, for the transposition gain that we can have with respect for the diffuse irradiation. And we can see how now in blue, instead of having like a continuous smooth line, we have some peaks that look a bit weird. And the same for hourly, we have the same stairs-like distribution. And here below, we have the same two intervals that we had before, 7 a.m. and 1 p.m. And we can see how now instead of having a smooth curve for the sub-hourly simulations, we have also peak and down, some peaks that go up and down. And for the irradiation, we also have some fluctuations that happen within 1 hour. So these two factors, again, are the ones that make different the irradiation that we will observe at the plane of array for hourly and sub-hourly simulations. And here, again, it's difficult to estimate if we are going to get lower or higher values, but we will observe some differences. And the higher variability on the transposition ratio, on the transposition gain for sub-hourly simulations will be observed due to the irradiance fluctuations that we have. Then the last loss that we observed was the one related to the clipping losses. As I mentioned at the beginning, it's something that we could expect due to the irradiance fluctuations that we have within 1 hour. As we know, in the inverter, we have the window of operation. If we exceed that value, we will be incurring into the clipping losses if we inject more DC than the one that the inverter accepts. And so what happens within 1 hour is that if we have irradiance fluctuations, for sub-hourly simulations, we may be entering in that limit that the inverter has and going down, which is the blue line that we can observe there. at some points the inverter is getting like the maximum limit that it has for the DC power, and in some others it's going down. As we have irradiance fluctuations, we will observe that curve. But for the hourly simulations, if we are averaging the amount of irradiance that we have within that hour, we may be thinking that we will then incur into any loss. So that will be the orange line, which is below the maximum power that the inverter accepts. And that's why always for sub-hourly simulations, we will get less energy, we will get lower clipping losses than with hourly simulations. So as conclusions, we could think that hourly meteorological data mask irradiance fluctuations that may happen within 1 hour. This has implications not only in the inverter clipping losses, as I just mentioned, but also on the transposition to the plane of array. Then the sun position that is used for hourly intervals may not be representative of the whole interval. We could think that the center of the interval is representative of what's happening in terms of sun position for 1 hour, but it's not, and it will have implications on the transposition to the plane of array for both components, for the diffuse and the beam component. Then that we will expect differences between hourly and sub-hourly simulations that will be higher for cloudy climates, higher interval resolution, and a higher DC-AC radius. Another conclusion will be that the use of sub-hourly meteorological data for the simplified Perth model will result in higher variability on the results, as we observed in the previous slides. And finally, that also this may affect some design parameters that we use for designing the PV plant. For example, for the DC-AC radio, when getting the optimal value, we may get a different value if we do that evaluation with hourly or sub-hourly meteorological data. Apart from that, there's one additional conclusion, which will be that for DC-based solutions, this will be like even more important, because in the end, the differences that we observed in the clipping losses will affect even more the design of these systems and the amount of energy that we can get to design these solutions. So that was all from my side. Now I think that we have time for the questions. Okay. So thank you. The first one. The first one was what is the difference in terms of energy production between using 15-minute and 1-minute data on average. I don't have that data like right now in my head. I will have to double check. But the bigger difference that we observed was between 16-minute and 15-minute simulations. Then, as I showed before in some graphs, for the irradiation, for 15-minute data, we could think that we will get lower irradiation when comparing to hourly simulations, but for 1 minute we were getting higher irradiation, so that will also affect. Then the second question, where is the metadata coming from for this study? Is it from satellite, time series TMY? Thank you. Well, the 15-minute data was from satellite data, and then for the 5-minute and 1-minute data, we took like data that was coming from more mathematical models that convert that data into 5-minute and 1-minute interval resolutions. The tracking angle is simulated in sub-hourly time steps. Yeah, so we evaluate all the intervals that happen with at minute level. If we are evaluating sub-hourly simulations, minute level, 15-minute or 5-minute, so the tracking angle is calculated for every interval. So we run the simulation for all the intervals that we have in the meteorological data. And I think that's all. We are on time. I thought I wouldn't be on time, but we are. Thank you.